Hey everyone, and welcome to another deep dive. Today, we're diving into a paper
Oh, yeah.
that's been called like one of the most important papers in AI research.
The big one.
Attention is all you need. You've probably heard of it. It introduced this thing called the transformer architecture.
Right.
And chances are you're using AI powered by transformers like every single day.
Probably without even knowing it.
But like, what makes them so special?
Yeah, that's the question.
That's what we're here to find out. We've got the original research paper,
Okay.
plus the Wikipedia page on it.
Nice.
Ready to go. So get ready to like really dive deep
Deep dive.
into how transformers work, why they've caused such a stir in the AI world,
Yeah, they really shook things up.
and like what their impact has been.
Hugely impactful.
But don't worry, we'll make sure to explain everything clearly without getting too bogged down in the technical stuff.
To keep it accessible. Yeah, I'm excited to really get into the nuts and bolts of this attention mechanism. It really changed.
Yeah.
Like how we think about processing this sequential data.
Okay, so before we get to transformers, we need to understand like what came before it set the stage for a long time. Recurrent neural networks, or RNNs.
Yeah, RNN.
They were like the standard for dealing with sequential data, like language.
Sure.
But they had some pretty big limitations.
Oh, they definitely did.
Right.
Absolutely.
Right.
Imagine like you're reading a book.
Okay.
You don't just process each word, like individually,
Yeah.
You think about the context, the relationships between words, even if they're like pages apart.
Yeah.
RNNs. I had a tough time with that. Especially with long sequences, they struggle to remember information from earlier parts of the sequence.
So it's like trying to follow a complex plot, but you can only remember the last few sentences you read.
Exactly. No wonder they ran into problems.
Yeah.
And this difficulty, this remembering long-range dependencies, it led to this thing called the vanishing gradient problem,
Oh, yeah, I've heard of that.
essentially.
Huh.
The signal that's used to train the network, it gets weaker and weaker as it travels through the sequence, so it makes it hard for the model to learn effectively.
So like the signal fades out?
Yeah, it's like a game of telephone. By the end, the message is totally garbled.
Makes sense. So there were attempts to like fix this.
Yeah, they tried, like with LSTM,
Yeah, LSTM
a
stuff.
special kind of RNN.
Yeah.
But then came the transformer, and it just
Yeah.
changed everything.
Completely different.
Totally. The transformer said goodbye to recurrence and put all its bets on this attention mechanism. And it's not just like a clever name, it's a fundamentally different way of like processing information.
Okay, so what exactly is attention and why is it such a big deal?
It's a big deal.
Yeah.
I know you've compared it to focusing on keywords when you're reading,
Yeah,
but I feel like there's more to it than that.
definitely is.
It's about more than just focusing. It's about understanding relationships.
Okay.
Think about how you analyze a sentence.
All right.
You instantly connect the subject to the verb. You understand how different clauses relate to each other, all without like consciously thinking about it.
Yeah.
Attention allows machines to do something similar.
So it's not just about picking out important words, it's about understanding the connections between them.
Precisely. And the transformer doesn't do this by analyzing the sequence like step by step like an RNN.
Yeah.
It looks at the entire input at once
The whole thing.
and figures out how every part relates to every other part. This ability to see these complex relationships, understand the context of each word or phrase, that's what makes attention so powerful.
That makes sense. But how does it actually work? What's going on like under the hood?
So, the core of the transformer's attention mechanism is something called scaled dot product attention.
Scaled dot product attention.
It involves some clever math using vectors
Yeah.
to represent different aspects of the input,
Okay.
which are called queries, keys, and values.
Queries, keys, and values.
Essentially, it allows the model to calculate a relevance score
Huh.
between different words or phrases based on
Exactly.
their meaning and position in the sentence.
Okay, I'm following so far. But I'm a visual learner. Is there a way to like picture how this scaled dot product attention works?
Absolutely. Imagine you have a table with all the words of your sentence. And for each word, you have a set of scores that tell you how much it relates to every other word in the sentence.
Okay.
These scores are calculated using the dot product of the query and key vectors, and then scaled down to prevent them from getting too large. This table of scores essentially represents the attention weights.
So the higher the score, the stronger the connection between two words.
Exactly. And these attention weights are then used to calculate a weighted sum of the value vectors, which gives us a new representation of each word that incorporates information about its relationship to other words in the sentence.
So instead of just processing words in isolation, The transformer creates a richer representation of each word by considering its context.
Yes.
I'm starting to see how this could be a game changer
It is. It truly is.
for understanding language.
But the innovation doesn't stop there.
Totally.
The paper also introduces multi-head attention.
Multi-head attention.
Instead of having just one set of attention weights, it uses multiple sets, each focusing on different aspects of the input.
So multiple sets of weights.
Think of it like having a team of experts
Okay.
analyzing the same text,
Yeah.
each paying attention to different nuances and relationships.
Got it. So it's like having multiple perspectives on the same information.
Exactly. That must lead to a much deeper understanding of the text.
Yeah, that makes sense. And this is where we start to see, like, the real advantages of transformers over RNNs.
This is where it gets really interesting.
All right. Let's dive into those advantages. Why is this attention mechanism so groundbreaking?
Well, for starters, it enables parallelization.
Parallelization.
Remember how RNNs were stuck? Processing sequences word by word with attention? The transformer can process the entire input sequence simultaneously.
Whoa.
This makes creating much faster, especially when dealing with massive data sets.
So instead of reading the book, one sentence at a time, it can process the entire book at once.
Pretty much.
That's a huge speed boost.
It is. It was a key enabler for training powerful AI systems on the massive data sets we have today. But speed isn't the only advantage.
Okay, what else?
Remember how we talked about RNNs struggling with long-range dependencies?
Yeah.
Well, transformers excel at capturing those connections between words, even if they're far apart in the sentence.
That makes sense. Given that attention lets the model see the entire input sequence at once.
Precisely. And this ability to capture long-range dependencies is crucial for understanding complex language.
So we have speed, and we have a deeper understanding of language. What else can transformers do?
Well, the authors didn't just make claims, they put the transformer to the test on machine translation tasks, specifically English to German and English to French.
Okay.
And the results were impressive.
How impressive are we talking?
The transformer achieved significantly better BLEU scores than any previous model. BLEU, or Bilingual Evaluation Understudy, is a metric that measures the quality of machine translation by comparing the output of the model to human-translated references.
So it's not just a theoretical concept, it actually delivers in practice.
It does. This was back in 2017.
Wow, so this was early days.
It was a pivotal moment in AI research. But the authors went even further.
Okay.
They predicted that the transformer's application would go far beyond translation.
Really? They already saw its potential in other areas.
They did. The paper specifically mentioned possibilities in fields like question answering.
Question answering.
Okay.
Look where we are today.
It's like they had a crystal ball.
Right.
Think about some of the big names in AI right now.
Like BERT, GPT,
GPT,
DALL-E.
They're all built on the transformer architecture.
It's true. This one paper sparked a revolution in AI.
Yeah.
And it's important to remember that these models are often specialized for particular tasks.
Right. Some, like BERT,
Yeah.
are encoder-only models designed to understand text, while others, like GPT, are decoder-only models focusing on generating text. And some models use a combination of both.
So it's a diverse landscape with the transformer at its core.
It is.
Wow. So attention is all you need. Wasn't just a catchy title, it was almost a prediction.
They were really onto something.
And speaking of the authors, there's an interesting human side to this story, isn't there?
Yes, there is. The Wikipedia page notes that all 8 authors of the paper have since left Google.
And many of them have founded their own AI companies.
It's true.
It really speaks to the impact of their work and the wave of innovation it inspired.
It does. They've gone on to shape the AI world in extraordinary ways.
Okay, let's take a pause here. In the next part of our deep dive, we'll get into some more of the details of the transformer architecture and how it's been used in different areas.
That's good.
Stay tuned.
I'm eager to dig a little deeper. This is just the beginning.
Welcome back.
Ready to unpack some more?
Of the magic behind transformers.
Absolutely. It's amazing how much ground this one paper covers. We talked about how attention revolutionized sequence processing. But there's a crucial aspect we haven't touched on yet.
What's that?
Positional information.
Yes. Unlike RNNs, which inherently process information sequentially, transformers look at the whole input at once.
The whole thing.
That creates a challenge.
How does the model know the order of the words if it's not reading them one after the other?
That's a great point. It's like shuffling a deck of cards. All the information is there, But the order is what gives it meaning.
Precisely. The authors of Attention is All You Need. They knew they had to address this. Their solution. Positional encodings.
Positional encodings.
Yeah.
So they basically gave each word a little note saying, hey, I belong over here.
That's a good way to visualize it.
Yeah.
These positional encodings are vectors, like numerical tags, that are added to the word embeddings to carry information about where each word sits within the sequence.
Interesting. So it's not just about what a word means, but where it is in the sentence.
Exactly. And they didn't just randomly assign numbers.
Yeah.
They used sine and cosine functions.
Sine and cosine. Those sound familiar. Weren't those something we used in trigonometry back in school?
Yeah.
What do they have to do with language?
It might seem surprising, but sine and cosine waves have some very useful properties. For representing positional information, they allow the model to easily learn relationships based on relative positions.
Relative positions. Could you give an example?
Sure. Imagine you have the words bird and sang. In a sentence, their exact positions might be the fifth and seventh words, but their relative position is that. Sang comes 2 words after bird. Sine and cosine functions make it easy for the model to learn this. 2 words after relationship, no matter where the words actually appear in the sentence.
So the transformer can understand that the bird sang and a beautiful blue bird happily sang have the same underlying structure, even though the words are arranged differently. That's pretty neat.
It is. These positional encodings are vital for the transformer's ability to understand the order of words and how they relate to each other.
No. You mentioned earlier that the paper tested the transformer on machine translation tasks, but they also explored something called English constituency parsing.
They did. And this really highlights the transformer's versatility. Constituency parsing. It's all about understanding the grammatical structure of a sentence.
Okay.
It's like taking a sentence and diagramming it, breaking it down into its core components, like noun phrases and verb phrases.
So it's like taking a deep dive into the grammar of a sentence.
Well, yeah. And the transformer was able to handle this task, too.
It was.
It did, surprisingly well.
Really?
They trained a transformer model on the Wall Street Journal section of the Pentry Bank.
Pentry Bank.
A massive data set used for training natural language processing models. And the results were excellent.
What were the results like?
It outperformed almost every other model that had been tested on that data set.
Wow.
And it even did well when trained on a much smaller data set, which is pretty remarkable.
So the transformer isn't just a one-trick pony. It's more like a Swiss Army knife of AI.
I love that analogy. Capable of tackling
all
sorts of challenges.
And that's a key takeaway from this paper. Attention is all you need. It wasn't just about creating a better machine translation model. It was about introducing a completely new way of thinking about sequential data processing, one with the potential to revolutionize a wide range of AI applications.
Right, and we've definitely seen that potential realized in the years since this paper was published.
But did the authors point out any limitations or areas for future research?
Yes, they did. One challenge they highlighted was handling very large inputs, like images and video. Traditional attention mechanisms can become computationally expensive when dealing with such high-dimensional data.
That makes sense. Images and videos are so much more complex than text.
Right, so the authors suggested exploring an local restricted attention mechanism.
Local restricted attention mechanism.
As a way to make attention more efficient for these types of inputs.
So instead of looking at the whole image at once, the model would focus on smaller, more relevant areas.
Precisely. It's similar to how our own visual attention works. We don't process every pixel of an image equally. We focus on the parts that are most important to us.
So building on the core concept of attention, but making it even smarter and more efficient.
Exactly. And that's one of the key directions in AI research today, finding ways to make attention more scalable and adaptable for a wider range of tasks and data types.
This paper from 2017 is still shaping the future of AI research, which is incredible.
It really is. The ideas presented in Attention is All You Need continue to inspire and drive innovation in the field.
Okay, we've covered a lot of ground today, but we're not done yet.
Right. We've only scratched the surface of models like BERT and GPT, and we haven't even touched on the broader impact of transformers on the AI landscape.
We'll save that for another deep dive in the next part. We'll wrap things up by summarizing the key takeaways from this paper and discussing what it all means for the future of AI.
I'm excited to see what insights we uncover. This journey through the world of Transformers has been fascinating.
Welcome back to the final part of our deep dive into attention is all you need. We've explored like all the inner workings of Transformers, from that attention mechanism to positional encodings, and we've seen how they've just taken the AI world by storm.
Completely revolutionized things. It's been quite a journey, and retracing the impact of this like revolutionary paper. Who could predicted that? A concept like attention would lead to such a massive transformation in AI.
It's mind-blowing.
It really is.
So as we wrap up, I'm curious to hear like your take on the big picture.
Okay, what are the key takeaways from attention is all you need that you think we should all remember?
Yeah, what are the big things people should take away?
Well, I think the most important takeaway is that it fundamentally changed how we process sequential data.
Changed how we process sequential data.
Yeah, the attention mechanism gave AI systems a new way.
Yep.
Like see the
They're
connections.
Doing relationships that were previously hidden within data.
Hidden within the data.
Leading to a huge leap forward in performance across a wide range of tasks. It's like we gave machines the ability to understand language and even images and video in a way that's much closer to how humans do it.
That's a great way to put it. And this shift from recurrent models to attention-based models has had a ripple effect throughout the field of AI.
Ripple effect throughout AI.
Yeah, it's not just about better machine translation. It's about opening up new possibilities in natural language processing, computer vision, and even fields like robotics.
And the authors of this paper, they had the foresight to see this coming.
They did. They clearly stated that attention could be applied to many different domains beyond language. And they were absolutely right.
They were right.
It's remarkable how they anticipated the broader impact of their work. The Transformer has become like a foundational architecture for so many AI systems today.
It planted a seed that has grown into an entire forest of intelligent machines.
A forest of AI.
Okay, so we've established that attention is all you need was a game changer. But where do we go from here? What are some of the open questions and challenges that still need to be addressed?
One of the biggest challenges is scalability.
Scalability.
We touched on this earlier. Attention mechanisms can become very computationally demanding when dealing with large inputs, especially things like high-resolution images and videos.
So finding ways to make attention more efficient is crucial for unlocking the full potential of Transformers in those areas.
Exactly. And there's a lot of exciting research happening right now to address this, exploring concepts like sparse attention.
Sparse attention?
Well, the model only attends to a small, relevant subset of the input.
And hierarchical attention.
Hierarchical attention.
The model processes information
at different levels of detail.
It's like we're trying to optimize the brain of these AI systems, making them smarter and more efficient at the same time.
That's a great analogy. There's also ongoing work to make Transformers more adaptable and robust so they can handle new situations and unexpected data without breaking down.
Sounds like the future of AI is going to be shaped by the ongoing evolution of the Transformers.
I think that's a safe bet. The ideas presented in Attention is All You Need have had a profound impact, and the journey is far from over.
Well, this has been a truly insightful deep dive into the world of Transformers.
It has. We've covered a lot of ground, from the fundamental concepts to the wider implications of this breakthrough paper.
We really have.
I completely agree. It's been a pleasure exploring this topic with you.
And thank you for joining us on this deep dive. Hopefully you've come away with a better understanding of how Transformers work, why they're such a big deal, and how they're shaping the future of AI. And remember, keep an eye out for those local restricted attention mechanisms the authors mentioned.
Yes, they might just be the key to unlocking the next generation of even more powerful and efficient AI systems.
Powerful and efficient AI systems. That's all for today. Thanks for listening, and we'll see you next time on The Deep Dive.